So now we can do some examples because we know this formula. Again, the formula is F equals mass times acceleration. So what force would require a 10 kilogram soccer ball to accelerate at 5 meters per second squared? Okay. Well, we're looking for force. It says what force. So F equals the mass, which was 10 kilograms, times the acceleration, okay, 5 meters per second squared. Multiply that out and you get 50. But what's the unit label? Okay, the 10 was in kilograms. The 5 was in meters per second squared with a direction. So our 50 is kilogram meters per second squared with a direction. Now that's a lot to say and a lot to write. So what we do is we can simplify this, okay, and call it a Newton. So our answer becomes 50 newtons with a direction. Okay, so 50 newtons with a direction. Let's do the second one. A toy car is pushed with 20 newtons of force. It has a mass of 4 kilograms. How fast does it accelerate? Again, our formula we know is F equals ma, okay, m times a. This time it says we have a force of 20 newtons. So 20 equals m. Do we have the m? Yes. Mass is 4. Equals 4 times a. That's what we need. We want to find the acceleration. So 4 times a. Okay? Divide both sides by 4. And you get a equals 5. Okay, 5 what? Well, it was in newtons. Okay, it was in newtons. So my acceleration is going to be meters per second squared with a direction. Okay, check for significant digits. We're good with 1. Okay, so the acceleration was 5 meters per second squared. All we're doing is filling in the letters. F equals ma, we're just filling in the letters. Okay, they're all variables. The last one seems a little bit more difficult, but really it's not. I have a mass of 77 kilograms. Okay, so that's going to be the m. How much do I weigh? Remember, weight is a measure of the force of gravity. So whenever you see weight, that's force. Okay, weight's the force of gravity. So again, F equals ma. Keep saying the same thing. Okay, I'm looking for weight, so I'm looking for the F. Okay, so F equals the m, mass it says was 77 kilograms. Okay, times the a. Uh-oh, I don't see an a in here. I don't see any other numbers. Well, what's it going to be then? All right, I'm on Earth. What's the acceleration of gravity downwards? We just did it. 9.8 meters per second squared. So I have 77 times 9.8. You do that and you get, it looks like it's 754.6 newtons. Remember, weight was in newtons because I was in kilograms and meters per second squared. I need to do my significant digits. 77 has 2, 9.8 has 2, so my answer can have 2. So 754.6 would round to 750 newtons. Okay, so I weigh 750 newtons. Okay. We're going to be doing a lot more examples of these in class. So don't worry, you're going to get lots and lots and lots of practice with this. Okay, on to Newton's third law. Newton's third law is one that you have heard lots and lots of times. Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. Okay, you might know it as, for every action, there is an equal and opposite reaction. Okay, that's this law. Okay, so all forces are going to act in pairs. That's the action and the reaction. If a force is exerted, another force occurs that is equal in size and opposite in direction. They're called action-reaction pairs. So if the guy here, he pushes on the wall with 100 newtons of force, okay, that would be the action. The reaction is going to be opposite and equal. So the wall pushes back on him with 100 newtons of force. Okay, we know it's equal. What if he was pushing with more force? Well, then the wall would fall down. What if the wall pushed back with more force? Well, then it'd push him down. Okay, it's equal and opposite. Okay, now what if the guy's on a skateboard like this girl? Okay, she pushes on the wall pushes on her, and she goes sliding across the room. Okay. So when you sit on a chair, you're applying a force on the chair. The chair is also applying a force back on you, equally and oppositely. That force is equal to your weight. Okay, so what's the action force? Okay, the action force is gravity pushing down on the chair with your weight. The reaction force is the chair pushing up on you. Are they equal? Yes. Again, he's not falling into the floor or he's not flying up into the ceiling. They are equal and opposite. Okay, now an important point down here. Remember, forces always occur in pairs, but the force pairs never act on the same object. Okay, the force pairs never act on the same object. That's a key thing. Remember, we had a picture similar to this, except I think we had two people pushing a piano. Okay, this guy pushes with 100 newtons of force to the right. This guy pushes with 100 newtons of force to the left. Does the refrigerator move? No. It's a balanced force. Okay, 0 newtons balanced force. There is no change in motion. Okay. Newton's third law isn't a balanced force. Okay, this is not an example of Newton's third law. Okay, because these forces aren't acting on the same object. He pushed the refrigerator, he pushed the refrigerator. Okay, they're pushing the same object, so they balance out. Okay, we look at the swimmer here. Okay, she pushes on the water pushes on her. So she goes forward. They're on different objects. She pushed the water pushed her. Two different objects, so that's why she can still go forward. Okay. A couple more Newton's third law examples. Let's say you have a balloon and you fill up the balloon and then you open it up. Okay, the action force is the air rushes downwards. So the reaction is the balloon goes up. That's the same thing for a rocket. So you see a rocket at the bottom of the picture. The exhaust pushes out that way, so the rocket goes up equally and oppositely that way. A bullet, the same thing. You fire a gun. The bullet goes that way, the action. The reaction is the gun kicks back. Okay, if you've ever fired a gun, you probably have experienced that kickback. Okay, that equal and opposite reaction. Bullet goes forward, gun goes back. Okay, a couple last ones, a little bit harder examples maybe. So what if I hit a ball with a baseball bat? Okay. The action force is obviously the ball, the bat hits the ball. So the reaction is the ball hits the bat. Can you feel the ball hitting the bat? Yes, hurts your hands maybe. Or you see in this picture, the baseball bat actually broke. Okay, the ball hit the baseball bat and broke the bat. Okay. Now, if he hits the ball, let's say he hits the ball, 500 feet out of the ballpark. Why didn't his bat go back 500 feet? We're going to talk about this more in class, but that's where Newton's second law comes in. Okay? the mass of the ball is a lot less than the mass of the bat, so the ball is going to go farther than the bat does. Think about the same thing with the gun. Let's say that I have a little pistol. The bullet goes half a mile, let's say. The gun kicks back, but it doesn't go half a mile, because the mass of the bullet is so much less than the mass of the gun. But now, what if I get a really, really big gun with a really, really big bullet? Okay, I fire the bullet forward, the kickback of the gun is a lot more. Okay, the bigger the mass of the bullet, the more the kickback is. It's still not kicking back half a mile because the gun is still a lot more massive than the bullet. And this last example really shows that. You see this little kid, he's kind of nervous. He's like, oh my God, you're not going to get the right answer. If I drop a ball, obviously the earth acts on the ball with a force. Okay, gravity. The ball falls down. What's the action and the reaction? Okay, the action is the earth pulling the ball down. What's the reaction? Okay, it has to be equal and opposite. If the earth pulls the ball down, then the ball pulls the earth up. The ball pulls the earth up. What? That has to be it though, right? If the earth pulls the ball down, then the ball pulls the earth up. Okay, equal and oppositely. Of course, the ball has a less mass, so it doesn't pull the earth up very much. Okay, a different mass. The earth moves only a fraction of a millimeter. And that's it for Newton's laws.